Hi everyone, welcome to lecture 34 of your electric circuit class. And lecture 34 is about power factor correction. The objectives of this lecture: the first objective is to understand the importance of power factor correction. And the second objective is to calculate the necessary capacitance value to raise the power factor to a desired value. So let us start with this topic, that is power factor correction. So power factor correction is achieved through the installation of a reactive element usually a capacitor in parallel with the load to raise the load's power factor to be close to unity. So we would like the power factor to be close to 1. So usually that, let's say if I have a load impedance here, and this over here is V load, and that is in RMS, then what we have to do to raise this power factor of the load is to install or connect a capacitor in parallel with that load. The idea that we are saying that usually a capacitor, because most loads, so we can write here, most loads are motors, which means that inductive. So the inductive, we need capacitive to cancel it out. So we will connect a capacitor in parallel with that load. So over here that I would like everybody to understand this point over here, because the motor, it has windings, and these windings are coils, and since that is or these are coils, that means they are inductances, which means that it is inductive load. So the idea of power factor correction is like this. So I have, for example, this is the power, this is our original Q, and we can call it Q1, that is P1. This is S1, because this is the power triangle. So the angle over here, that is theta 1, so which is the angle of the load. So now, if we would like to correct this power factor, that means we have to really decrease the angle theta 1, because when the angle becomes 0, then cosine 0 is 1, which is the power factor. In this case, it will be unity, and that is the desired value, or the best value, let's say. So the other one is when we are adding, let's say, the capacitor, if we add that much up to here, then that is the reactive power coming from the capacitor. Then that means we will have our theta 2 is here, our S2 is here, and this is our P1, P2, which means that in this case P1 is equal to P2, and we can say that is equal to P, because look at this, the value that we alter or we change is the reactive power, so we did not touch the real power at all. So since this over here is S2 and this is P2, then this value from here to here, that is our Q2, which means that really Q1 is equal to QC plus Q2, or we can say that Q2 is equal to Q1 minus QC. So now let us define these values here, where first one is P1, average power of the load, and that is in watts. Q1 is reactive power of the load, and that is in volt ampere reactive. Then we have S1. S1 is the apparent power of the load, and that is in volt ampere. Theta 1 is the power factor angle of the load, and that is in degrees. So now, after the addition of the capacitance, which is after what we call compensation, we can define the following. P2, average power after compensation. and that is in watts. Q2, reactive power after compensation in volt ampere reactive. S2 is apparent power after compensation, and that is in volt ampere. And theta 2 the power factor angle after compensation. And that is, of course, in degrees. It is called the desired power factor angle. And QC is the reactive power of the capacitor. So based on that, based on the power triangle, we can say tangent theta 1 is equal to Q1 over P1. And this will give us Q1 is equal to P1 tangent theta 1. And this is our first equation. And we have tangent theta 2 is equal to Q2 over P2. And this will give us Q2 is equal to P2 tangent theta 2. And this is our second equation. However, if you look, we have not touched the P. So P is not altered at all. That means P1 is equal to P2, and we can call that as P. And this is, let's say, our third equation. So now if we substitute the third equation into equation 1 and equation 2, this is what we are going to get. That Q1 is equal to P tangent theta 1, and the Q2 is equal to P tangent theta 2. So now the reduction in reactive power is caused by the addition of the capacitor. So the value of the reactive power of the capacitor is QC is equal to Q1 minus Q2, because this is over here the original Q of the load, and this over here the resulted reactive power after compensation, because the resulted reactive power after compensation is caused by the addition of the capacitor. So in this case, we can substitute for Q1 and Q2. So that means this is equal to P tangent theta 1 minus P tangent theta 2, which means that is equal to P multiplied by tangent theta 1 minus tangent theta 2. And this is the reactive power of the capacitor required to correct a power factor to a desired value. Theta 1 is the angle of the original load, and theta 2 is the desired power factor angle. So now, when we look at QC, that is equal to VL RMS squared divided by X sub C, right? This is how we can get a reactive power when the voltage across the reactance is known. And this is equal to VL RMS squared divided by our X sub C is 1 over omega C. So this will end up with omega C VL RMS squared. So if we solve for C from this equation, we are going to get C is equal to QC divided by omega VL RMS squared. So now we just substitute for the QC, and that is equal to P multiplied by tangent theta 1 minus tangent theta 2 divided by omega V load RMS squared. And this is the equation that you can use to find the value of the capacitance necessary to raise a power factor to an angle of theta 2. So now, notes. VLRMS, this is the voltage across the load. Theta 1 is the original load power factor angle. Theta 2 is the desired power factor angle. So let us take an example here to show the application of these equations. We do have a load, and this load consumes 5 kilowatts at 0.8 power factor lagging. The voltage across the load is 208 volts RMS at 60 hertz. we would like to determine the value of the capacitance necessary to raise the power factor to unity. So when we are saying that power factor unity, that is PF is equal to 1. So let us do the following, that P is equal to 5,000 watts. Now PF1 is equal to zero point 0.8. That means our theta 1 is equal to the inverse cosine of PF1, and that is equal to inverse cosine of 0.8, and that is 36.87 degrees. So now we got theta 1. So that is from the original load. Then we have to go with our PF2, power factor 2, that is 1, because this is here to raise the power factor to unity. That means theta 2 is equal to the inverse cosine of 1. And or inverse cosine of PF2, and that is the inverse cosine of 1, and that is equal to 0 degrees. That means this over here is our what? Theta 2, right? The desired one. So now our omega is equal to pi f, which is 2 pi, and the frequency is given as 60 hertz, and that will be 377 radians per second. So now all the values in the equation are known. So from that we can find the value of our capacitance. So that is P tangent theta 1 minus tangent theta 2 divided by omega VL RMS squared. So P is 5,000 multiplied by tangent theta 1 is 36.87 degrees minus tangent 0, which is theta 2, divided by 377 times the voltage across the load. It is given as 208 volts RMS, and that is square. And our value here is 229.9 microfarad. What that means? That means if we connect a capacitor of a value of 200, almost 230 microfarad in parallel with that load, we will guarantee a power factor to be unity. Why power factor correction is important? Look at this. When I have this triangle here, I have this P, I have this Q, and I have this S, and of course that is our angle theta. So the lower here, the or why when we can say that when theta, let's say, reaches 0 degrees, that means our P and S are equal, right? So usually the power utility companies not only here in United States, but everywhere in the world. When they send the bill, they send that bill as kilowatt hour, which means they claim to, since the P is in kilowatt and then the energy in kilowatt hour, they are claiming that they are charging you for this P, while honestly that they are charging you for this S. Okay, so they are charging you for S. So that's why when we correct the power factor, let's say to be unity, then our P and S are equal, which means that you are maximizing your benefit out of that, let's say, energy consumption. Clear? I hope that message is clear. Let us go over another example here. Determine the necessary capacitance to raise the power factor of the combined load to 0.95 power factor lagging. And our circuit look like this. That is Vs. We do have the first load here, and this is load 1, which is 12 kilowatts, 0.87 power factor lagging. Load 2, 24 kVA, 0.9 power factor lagging, and the voltage across the load is 240 with angle 0 volts RMS. So what we are trying to do is to connect a capacitor in parallel with this combined load. So first of all that, we have to combine both loads together. The idea to combine both loads, we have to find the complex power of each and then add them together. So to combine loads, find the complex power of each load, then add them together. Because it doesn't matter the connection of these loads if they are in parallel or series parallel, because as you know, if they are in parallel, the voltage is the same. If they are in series, the current is the same. So when it comes to power or complex power, doesn't matter the connection. So you will just combine them together by adding them together. So now, from that, from load 1, we have the P of load 1 is given as a 12,000 Because look at this, you have to pay attention to the unit here. What is the one that given? Because as you know, we do have the power triangle. So in this case, since the unit is kilowatt, that means the power of load 1, which is the average power of load 1, is given. If you look at load 2, that is in kVA, which is 24 kVA. That means that is not the average power, that is the apparent power is given for load 2. So we'll go back to complete load 1. So the power of load 1 is 12,000 watts. The power factor of load 1, that is 0.87, which is lagging, right? Then that will give us our theta of load 1 is equal to the inverse cosine of 0.87, and that is equal to 29.54 degrees. So from that, we can say our SL1, which is the apparent power, that is PL1 divided by cosine of theta L1. And that is equal to PL1 divided by power factor of load 1. And that is equal to 12,000 divided by 0.87. And that is equal to 13,793 volt ampere. So this is our apparent power. So now to get our complex power of load 1, that is equal to the S of load 1 with angle of theta load 1. And this is equal to 13,793 with an angle of 29.54. And you see, because it is lagging, so for the complex power, our angle is positive. And in rectangular form, this is equal to 12,000 plus J 6,800, and that is in volt ampere. So this is our SL1. Now we go to load 2. Of course that you can go with a different route, and instead of that going with this method. Like, as you know that the P of load 1 is given as a 12,000, and the angle we found it to be 29.54, then our real power is 12,000. Our reactive power, I can go with what? Let's say that we have, this is the power triangle, the P is known, the angle is known, we need this, right? This is not known. Then you can go with tangent theta is equal to Q over P, right? Which means you will be able to find the Q. And when you find the Q and you have the P, then you can end up with this value anyway. For load 2, if you look at the given value here, as what we said, that is in kilovolt ampere. That means this is the apparent power. So the apparent power of load 2 is given as 24,000 volt ampere. So power factor of load 2 is given as 0.9. So that will give us theta of load 2 is the inverse cosine of 0.9, and that is equal to 25.84 degrees. So from that we can get our SL2, which is the complex power, that is SL2 with angle theta L2, and this is equal to 24,000 20,000 with an angle of 25.84 degrees, and that is volt ampere. And when we convert to rectangular form, that will be 21,600 plus J 10,460. So now we have load 1 and load 2. So we can say the total load or the combined load as S total is equal to S1 plus S2, and that is equal to our value. The first one is 12,000 plus J 6,800 plus S2 is 21,600 plus J 10,460, and the answer here is 33,600 plus J 17,260 volt ampere. So now this over here is the load that we need to correct because it is the combined load. So we can say that P1 is equal to P2 is equal to P, and in this case it is this value here. So 33,600 watts. Our theta 1 is equal to what? Is equal to the angle of this ST. So what is the angle of this ST? If I want to go with converting this to a polar form, we are gonna get 37,774 with an angle of 27.2 degrees. So now our theta 1 is really this angle here. So that is 27.2 degrees. So now in our problem here, we said that raise the power factor to what? 0.95 lagging. That means this is our theta, the power factor, which is belong to theta 2. This is the desired one. So we can say PF2 is equal to 0.95, which means our theta 2 is the inverse of cosine of 0.95, and that is equal to 18.19 degrees. So our omega is equal to 2 pi f, and that is 2 pi times 60, which is equal to 377 radians per second. If in any problem in AC, if you are looking, let's say, to find values and the frequency is not given, then you have to assume that frequency to be the operating frequency in United States, and that is 60 Hertz. So now our C is equal to P tangent theta 1 minus tangent theta 2 divided by omega VL RMS squared, and that is equal to 33,600, which is the real part of the combined complex power, times tangent theta 1 is 27.2, which is the angle of the combined load, minus tangent theta 2, which is 18.19. This is what we like our capacitor to correct the power factor to 0.95 lagging, so the corresponding angle is 18.19 divided by 377 times our voltage. If you look at our circuit, that voltage is across the load, so that is 240 squared, and the answer here is 286 microfarad. Please pay attention to the following. If I have a system like this, this is, for example, 120 with angle 0 volt RMS. This is, let's say, 4 plus J5. This is, let's say, 2 plus J2. And this is, let's say, 1 plus J3. And we are saying that this over here is our load. So the VLRMS does not equal to 120 with angle 0. Why is that? Because there is a voltage drop over here. So we said that VLRMS must be the voltage across the load. So that means this 4 plus J5, that is transmission line. So this is our load over here. So that means I need to find the VLRMS. How to find that? You combine these two impedances, then you will find the voltage drop across that combined load through voltage division, and then that voltage is the voltage to be used in the capacitance, let's say, equation for the power factor correction. Okay, don't forget that. So when you have loads, you have to get your total, let's say, complex power. This is how you can combine the loads when you are given power quantities and power factors. So find the complex power of each load and then you add them together to get the combined load. Please do not forget that. So now, by that, this lecture is done, and this is your homework for this lecture. 2 problems, and thank you for watching.